Okay, good. So I haven't got any kind of visual aids or anything, so I'll just shut that off and have a lovely blue screen behind me. What I'm going to talk about really is kind of taking a hackerish approach to mathematical discovery, why you should and how you can, with an example from something that I did recently. And I don't know how long it's going to take me. I haven't prepared this very thoroughly, but sometime in the region kind of 5 to 10 minutes probably. So why you should? Well, first of all, I mean, maybe not everyone agrees with this, but I think discovering new mathematical things is one of the most brilliant things that you can do, because for a brief period, you know something that nobody else knows. And that is, I think, a very exciting feeling. It's not as inaccessible as you might think. There are lots of things that can be discovered that you don't need kind of to spend years and years studying to get to the point where you can understand them and start to think about them. And some of them are relatively accessible to being solved. Of course, having discovered something, you can't resist the urge to tell people about it, so that kind of private knowledge doesn't last for very long. And other people aren't nearly as interested usually as you are, because of course it's more fun to have discovered something yourself than to hear about something that someone else has discovered. And the other thing is that, you know, pure mathematicians as a whole, they're kind of chalk and blackboard kind of people, right? Pencil and paper. It's a pretty old school profession on the whole. I mean, you know, they do use, kind of more applied mathematicians use software, and it's starting to creep in a little bit to the more kind of traditional pure mathematical world, but it's still really, you know, pure mathematicians are mostly not hackers, and hackers are mostly speaking not pure mathematicians, and that kind of creates opportunities. There are certain kinds of problems that are much more just vulnerable to a sort of hacker's approach than to a pencil and paper approach. And so that creates opportunities for people like us to discover things that the pure mathematicians might have missed with their blackboards. I mean, the particular example that I have in mind is something that I did kind of recently, like in the last couple of weeks. It was a problem that I heard about on Reddit, and as far as I know, the best kind of theoretical result on this problem prior to this was the proof was written by an anonymous user on 4chan. So it's fairly atypical for mathematical proofs. It's very unique in my experience for mathematical proofs. And the problem is the following one. So ambulances, right? Like fire engines, they go nee-no, nee-no, nee-no. Are they going nee-no, or are they going nor-nee? Well, it's both, isn't it? They're doing both. And so what's the shorter sequence of nees and nors that you need in order to get both possibilities in there? Nee, nor, nee. There, you've got it. You've got nee, nor, the first two. Nor, nee, the second and the third. Both the possibilities are in there. Okay, but fire engines, you know, I'm not an expert on sirens. Maybe someone here is and can tell me more details about sirens. But, you know, when you hear sirens kind of on the streets of London, it's not just nees and nors. There are all kinds of wibbles and other sounds. So, I mean, suppose there were 3 sounds that a fire engine can make, nee, nor, wibble. Then there are more possible permutations of that. You've got, okay, bear with me, nee, nor, wibble. That's one of them. Nee, wibble, nor. That's number 2. There should be 6. So let's see if this works. Nor, nee, wibble. Nor, wibble, nee. Wibble, nee, nor. Wibble, nor, nee. Right, 6 possibilities. So what is the shortest kind of sequence of nees and nors and wibbles that the fire engine can play that will get all those possibilities in there somewhere? So I know the answer to this. I'll see if I can do it. I'm going to have to think about this for a second. Nee, nor, wibble, nee. Nor, nee, wibble, nor, nee. Right, so if you think about, thank you. So I mean, if you think about that, you'll see that all 6 possibilities have been included in there somewhere, but there were only 9 sounds in that sequence. So it's more efficient than just doing all the 6 possibilities one by one. You've saved some effort. And there's a kind of algorithm that you can use to construct this kind of sequence with different numbers of sounds. So super permutations was my ill-considered title because someone in about 1993 decided that super permutations were what they wanted to call these sequences because they contain all the possible permutations. So they're like super because they contain them all, I guess is the idea, like a superset. So anyway, you can construct super permutations. And it turns out that for 4 symbols, I'm not going to attempt to do this. I'm sorry. I did think about it, but I'd need to practice lots more than I have to do it. But for 4 symbols, it is, what's 24 plus 9? It must be 33. 33 sounds long is the shortest sequence of 5 sounds that contains all the possibilities. And in general, the construction goes, it goes, do you all know about what a factorial is? Yeah. Okay. So it's a sum of factorials. So for 5 sounds, it would be 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial. And until about the spring of this year, it was unknown whether this kind of, if you do 1 factorial plus 2 factorial plus 3 up to 5 factorial, the answer is 153. And so you can construct a sequence of 153. I don't know, what would the 5 sounds be? It would be like do, re, mi, la, so. Is that right? If it was maybe more of a musical kind of fire engine than the traditional ones. So that there would be there's a sequence of 153 do, re, mi, la, so. But there's a proof, as I say, that the only written version of this proof that I'm aware of was written by an anonymous 4chan user, which proves that the shortest possible sequence would be 152 sounds long. So there was this kind of unknown question: was it 152 or 153, the shortest one for 5 sounds? And a bloke whose day job is designing processors for Intel, but who obviously is a mathematical hobbyist, wrote a C program that used a relatively clever kind of technique to find out all the possible shortest 5-symbol things. And anyway, the answer is 153 is the shortest, but there are 8 different ways of doing it, not just the obvious way. So then, am I out of time?
You've got another 3 minutes.
Another 3 minutes, perfect, okay. So there's something called the traveling salesman problem. So there's a salesman who has to travel around to lots of different cities to sell his underwear to all the people of these different cities. And he wants to do this in the most efficient way possible. So he wants the route that takes the shortest distance, that visits all these cities, and then returns to where he started. And so although maybe it's not obvious, this particular problem is kind of the same problem, really, because your cities are all the different permutations, and the length of the route is the number of different sounds that you had to do to make the next one. So you want to make all the different permutations via the shortest possible route. So basically, this is an instance of the traveling salesman problem. And it also turns out that very, very smart people have been working out ways to solve the traveling salesman problem ever since some guys at Rand Corporation in the 1950s first kind of started tackling this. And it's really, really well studied, and there are really, really fucking good algorithms for doing it, which you can download for free, and they have a competition every year to see which one's the best. And so the problem for 6 symbols was totally unknown, but I kind of noticed that it was the same as the traveling salesman problem. So I downloaded a program called LKH, which finds solutions to the traveling salesman problem. And I, worked out its input syntax and fed this thing into it, and I left it running overnight. And then when I woke up the next morning, it had disproved this 20-year-old conjecture that the shortest thing for 6 symbols would be 673 symbols long, was the conjecture, I think, if you add it up. But it's not true. It's not true at all. There's one that's 672 symbols long that had gone undiscovered for 20 years that actually you can discover in one night just by kind of reading the manual for a C program and leaving it running overnight. So that's really the end of the story. Thanks.
Anyone have any questions for Robin?
I uploaded a kind of 3-page paper to the archive, yeah. So it's not technically published, but good enough, I think. What?
One right at the back, two at the back. You start by the door.
Sorry? I did submit an edit to the online encyclopedia of integer sequences, yes, so that there is a sequence related to this problem, which said that it was conjectured to be equal to this other sequence, which is the sum of factorials, and I submitted an edit saying it was conjectured to be equal to that sequence, but actually it isn't, and included a reference to my thing, yeah.
Cool. And one more question at the back.
I've considered it, yeah. I left it running for a few days, but it didn't really seem to be getting anywhere even close to the conjectured bound. So I think some more intelligent approach is likely to be needed just for 7, as far as I can. So, I mean, the other thing that's unknown is what the actual minimum is for 6. So the program that I use is a heuristic solver. It just searches for solutions, but it doesn't prove that they're minimal. I tried an exact solver that proves that the solutions are minimal, and it ran for a week and then crashed. So I still don't know the answer to that.
Cool, thank you. Afraid I've run out of time, so can I